In this lesson, we are going to talk about the definition of derivatives. And the basic idea is that derivative means slope. And we know that slope is rise over run. And so since we know how to find the slope, that means we know how to find the derivative. Consider, for example, the function f at x equals 5. This is the constant function, and all of the y values are going to be at 5. So here's a sketch of the graph. Two of the points it passes through are 0, 5 and 5, 5. And we can see that the slope of our horizontal line is 0. And so for this function, we would say f prime of x equals 0. And I'm going to write this on the next page, but that's the notation. That's one way to write derivative of a function is f prime. Okay, let's do a second example. Let's let g of x be the line negative 2x plus 5. We know that the graph passes through the point 0, 5 and the point 1, 3. And we see that the line is going downhill from left to right. Lines have constant slope, and so the slope of this line is always negative 2. And so for this one, we would say g prime of x equals negative 2. So first we're going to look at notation. If y equals f at x, the notation to write the derivative of f at x, there's actually several ways to do that. The most popular is f prime at x. So we read that f prime of x. But we could also write df dx. So the d is a shorthand way of saying difference of. So the change in the f divided by the change in the x. Because remember, slope equals rise over run. And you may have seen people write delta y over delta x for slope, maybe. And delta and d start with the same letter. We might also write dy dx. We might write y prime. We could write d dx of f at x, or of f, and we could also write d dx of y. So one thing I want to note is that determining the derivative is a function itself, and each input for finding the derivative is a function, and each output is a function. Most likely the output will be a different function than the input, but sometimes it's not. Sometimes they are exactly the same. So let's find the derivative of f at x, where f at x equals x squared. And at this point in the course, I am asking you to use the definition of the derivative. So let's sketch a graph of y equals x squared, passes through the point 0, 0, 1, 1, and negative 1, 1. The slope is not a constant for this parabola. Lines have constant slope, but this graph is not a line, so it does not have constant slope. So we are going to find the slope at a point by looking at the slope of secant lines. Secant lines are lines that pass through 2 points, or at least 2 points, of our graph. And so this green line that I drew in is a secant line that passes through the point 1, 1 and the point c squared. And so we can find the slope of the secant line by calculating rise over run. The rise is the difference in our y values. So I'm going to write that as c squared minus 1. And the run is the difference in our x values. So c minus 1. And if we simplify this, the numerator factors as c plus 1 times c minus 1. The factors of c minus 1 in the numerator and denominator cancel. And so we find that the slope of this secant line is just c plus 1. To find the slope at the point 1, 1, we're going to take the limit as c gets closer and closer to 1 of the slope of this secant line, and we get 2. And that is called a tangent line. And so we would say the slope at the point 1, 1 is 2, and that red line is called a tangent line. And so that's a slope through a single point. It's the limit of the slopes of the secant lines. So let's find the slope of f at x equals x squared at a different point. Let's look at the point 2, 4. So again, here's the graph, and I'm just going to plot the point 2, 4. I need a second point to be able to draw the secant line, and last time I used green for that, so I'll just write over this in green, c squared. The slope of the secant line is going to be c squared minus 4 over c minus 2, because that is our change in the y values over the change in the x values, or the rise over the run. To simplify, the numerator factors as c plus 2 times c minus 2, common factor of c minus 2 in the numerator and denominator, so this simplifies as c plus 2, and the slope of the graph at the point 2, 4 is going to be the limit of the secant line slope. So it's the limit as c goes to 2 of c plus 2, which equals 4. And we can continue to repeat this process for every single point that is on our parabola, but that seems very tedious. And so let's generalize how to find the derivative at any point. So let's find the derivative of f at x at an arbitrary point x squared. So there's my parabola, and I'm just going to put x squared on the picture just so that it's easy for us to see. I need a second point, c squared, and I draw the secant line between those 2 points. The slope of the secant line is going to equal c squared minus x squared divided by c minus x, because that is rise over run, or change in y values divided by change in x values. If we simplify this fraction, the numerator factors as c plus x times c minus x. The denominator is c minus x. I have a common factor of the numerator and denominator of c minus x, so that cancels out. And we're left with the slope of the secant line being c plus x. To find the slope of the tangent line, so at the point x squared, we're just going to take the limit as c goes to x. And that is what we call f prime of x, or the derivative. So the limit as c goes to x of c plus x equals x plus x, or 2 times x. And if we go back and think about the different points that we had before at 1, 1, we found y prime equal to 2 times 1. Or, well, we found it to equal 2, and that's the same thing as 2 times 1. And then we did a second example at the point 2, 4. We found y prime to equal 4, and that's the same thing as 2 times 2. So it seems like we have found a general rule for the derivative of x squared. So here we write the definition of a derivative. F prime of x equals the limit as c goes to x of f at c minus f at x all over c minus x. Derivative is slope. And so we are looking at the slope of secant lines and taking the limit as one of the points gets closer to the other point. A second way of writing this derivative is the limit as h goes to 0 of f at x plus h minus f at x, all divided by h. And that is, let's say that we have the point x, f at x, and another point c, f at c. And we're trying to find the slope of this secant line. We know rise over run is our slope, but what if we call h the horizontal distance of this rise over run? And so if we let h equal c minus x, we have a different way of writing the definition of a derivative. But they will get us to the exact same place. And so to do an example with the second way of writing slope, let's find the derivative of y equals negative 2x plus 5. We already know from looking at this earlier that y prime is going to equal negative 2 because the graph is a line and derivative means slope. So the slope of that line was negative 2, so the derivative has to be negative 2. So using the definition of the derivative though, y prime equals the limit as h goes to 0 of f at x plus h minus f at x, all divided by h. And you may recognize this as it's called a difference quotient that sometimes people see in a college algebra class. So simplifying the numerator, we get the limit as h goes to 0 of negative 2x minus 2h plus 5 plus 2x minus 5, all divided by h. And looking at what cancels out, negative 2x plus 2x equals 0, and positive 5 minus 5 also equals 0. And so this simplifies as negative 2h divided by h. There's a common factor of h in the numerator and denominator, so this is the limit as h goes to 0 of negative 2, and the limit of a constant is just the constant itself, so negative 2. And so now we have proven with the definition of a derivative that the slope of the line y equals negative 2x plus 5 is really negative 2. So the biggest thing I want you to remember is that derivative is slope.